This presentation is delivered by the Stanford Center for Professional Development.
Hey, welcome to Wednesday. Things that are happening, we're talking about sorting. We got lots of sorting to talk about today, some more sorting to talk about on Friday. So I'm going to pick up where I left off on Monday, and this was the code for the selection sort algorithm. And in fact, actually, I'm not going to, I'm going to be showing the code for each of the algorithms that I'm using here, but I'm going to encourage you to not actually get really focused on the details of the code. This is actually one of those places where the code is an embodiment of the idea, and the idea is the one that actually we're interested in studying, which is the approach it takes to sorting, how it decides to get that data in sorted order, and then how that algorithm performs, and the kind of details of where it decides to +1 and -1 and less than is actually a little bit less important for this particular topic. So what I'm going to show you actually is a little demo of some of this code in action that's done using our graphics library, just to show you what's going on. And so this is the selection sort code, that the outer loop of which selects the smallest of what remains from the position I to the end of the array, and then swaps it into position after it's done that finding. So this inner loop is basically just a min finder, finding the minimum index element from I to the n. And so I'm going to watch this code step through, so you can see as it moves j down, which is bopping by in green, it's actually updating this kind of min, the blue pointer there that says, well, what's the min I've seen so far? Early on it was 92, then it bumped down to 45, then it bumped down to 41, then 28, then 8. And finally we got to the end, it found nothing smaller. It says, okay, that must be where the min is. Let me move that guy to the very front. So exchanges those two guys, swapping that one back in there. Now, we know we have the very smallest one out of the way. It's in the right spot. We have nothing more to do with that. There's no changes that'll need to be made to anything to the left of I. And we do the same operation again. Select from the remaining n-1 elements the minimum element. So watch the green sort of finger move down while the blue finger kind of stays behind on the smallest it's seen so far. It says, okay, well then 15 is it. Swap that guy up into the second slot. Do it again, right? Keep doing this, right? Working its way down. And then as you see, the array is kind of growing from the left to the right. The smallest, most elements, right, being picked off and selected and moved out, and then leaving the larger ones kind of over here in a little bit of a jumbled mess to get sorted out in the later iterations of those loops. So there is select and sort in action, right, doing its thing. Okay. Let me do another little demo with you, because there's lots of different ways to look at these things. I'm going to do one that actually can do slightly bigger ones. And so I'm going to set this guy up, and it's going to show, in this case, the red moving, right, and it holding on to the smallest it's seen, updating as it finds smaller ones, moving it to the front. And then I'm actually going to speed it up a little bit, just to kind of see it go a little faster. And so you'll note that it took in this case, and it does a little bit of counting that we're going to look at in the analysis in a minute, about a lot of comparisons and not so many moves. That's actually kind of the model behind selection sort, is to do a lot of testing. That first iteration looks at every one of the n elements to find the smallest, and then it does one move to pull it into position. Then it does the same thing again, does another pass looking at this time only n-1 elements remain, but doing another full set of comparisons to decide who's the smallest of what remains, and then swapping out to the front. So it's taking a strategy that seems to indicate that comparison, right, is the operation it's going to do a lot of, but a very few number of moves as a result, because once it identifies where something goes, it pulls it out, gets it to the front, and doesn't do a lot of shuffling around. If I put kind of a higher number of things in here and let it go, it appears to kind of move very slowly at first, right, because it's doing a lot of work to find those small ones and then move them down to the front. But as it gets further along, it will tend to kind of speed up toward the end, and that's because in subsequent iterations, right, there's fewer of the elements remaining to look at, and so kind of a tiny little portion that's been sorted so far, the first 4. If I think I let this go, it'll go way too fast. Yeah, it'll go way too fast to see. And there's one other thing I want to show you, because I'm going to add in the option for sound. So One thing to learn a little bit about how to visualize sorts, right? I think that this kind of technique sometimes is easier to look at than the code, is to see how it's putting things into order. Several years ago, I had a student who actually was blind, and these visualizations do squat for someone who's blind, it turns out. So she helped me work out some ideas about how to do a different sort of interface, one that visualizes it using one of your different senses, which is through sound. And so the change I've made to the code here will play a tone each time it's moving an element. And the frequency of that tone is related to the height of the bar. So the smaller height bars are lower frequency, so lower tones, and then the taller bars have a higher frequency, higher pitch to them. And so you'll hear the movement of the bars being expressed with this tone movement. Getting sound? There we go. No, we're not getting sound though. Let's try. No, we're not getting sound at all. There we go. I'm getting sound now. How about you? Well, that's true. It is only when they move. That's a very good point. What about you? I have it running a little bit slower than I'm thinking. I'm like. There we go. I can get it to. All right, let's try it. Now we're. I feel like we're hearing something. We're still. Definitely getting sound now. Okay, now it's going to be maybe a little loud. There we go. So the march of the low order tones kind of getting moved into place, doing a lot of comparison, and then you'll hear kind of the speed up I talked about. Toward the end is the later iterations. Finishing it up. So giving you kind of a little memory for sort of what is the action of selection sort. The small amount of tones and the kind of sparse distance between them shows that it's doing a lot of work in between each of those moves, right? And then the fact that the tones kind of advance from low to high tells you that it's working on the smaller values up to the larger values, kind of working its way to the end, and that's speeding up, it closing in on the remaining ones as it gets to the end. Kind of neat. I left that around because even if you can see it, you can also hear it, and that may help something. What we're going to look at is, well, how much work does it do? So if I go back and look at the code just to refresh what's going on, right, this inner loop is doing the comparisons all the way to find the min elements, and so this is going to iterate n-1 times on the first iteration, then n-2, then n-3, and all the way down. Those final iterations, 3 to look at, 2 to look at, 1 to look at, and then 1 swap outside that. And so what I actually have here is the sum of the values. n-1 compares plus 1 swap, n-2 compares plus 1 swap. So a bunch of swaps, but then actually the terms I'm looking at here, the number of comparisons, the sum of the numbers 1 to n-1 is what we're trying to compute here. And then if you've seen this sum, the arithmetic sum or the Gaussian sum, you may already know how to solve it, but I just kind of showed you how to do the math to work it out, which is the term you're looking for is this sum. If you add it to itself but rearrange the sequence of the terms so that they cancel each other out, you'll see that the n-1 plus 1 gives you an n, and that what you end up with is n-1 n's being added together is what the sum of this sequence against itself is, and so we can divide by 2 to get the answer we're looking for. So we have a 1/2 n squared minus n term, which in the big O world, right, just comes down to n squared. So it tells us it's a quadratic sort, right, that we would expect that if it took a certain amount of time to do 100, 3 seconds, then if we double that input, we expect it to take 4 times as long. So if it was 3 seconds before, it's 12 seconds now. So growing as a parabola, kind of fairly sharp, steep curve to get through things. All right, so let me give you an alternative algorithm to this. Just to kind of think, that's kind of going to be the theme is, well, that's one way to do it, and that has certain properties. Let's look at another way, and then maybe we'll have some opportunity to compare and contrast these two different approaches to see what kind of trade-offs they make in terms of algorithmic choices. So the way you might handle a deck of sorting in order of cards. So if I'm handing out cards to people, you're getting each card in turn. That one way people do that is they pick up the first card and it kind of, you assume it's trivially sorted, right? It's in the right place. You pick up the next card and you decide, well, where does it go relative to the one you just had? Maybe you're just sorting them in number order and you say, okay, well, it's greater than it. It goes on this side. You pick up your next one and it's like it goes in between them. And so you're inserting each new element into the position of the ones that are already sorted. And so if you imagine applying that same thing in terms of computer talk in a vector sense, is you could imagine kind of taking the vector, assuming that the first element is sorted, then looking at the second one and deciding, well, where does it go relative to the ones already sorted, the ones to my left, and in kind of moving it into position, shuffling over to open up that space it's going to go into, and then just extending that as you go further and further down the vector, taking each subsequent element and inserting it into the ones to its left to make a sorted array kind of grow from the left side. So it grows from the left somewhat similar to selection sort, but actually will look a little bit different based on how it's doing its strategy here. So let me give you the insertion sort code. So my outer loop is looking at the element at index 1 to the element at the final index, array size minus 1. And it copies that into this variable current to work with. And then this inner loop is doing a down 2 loop. So it's actually backing up from the position j over, starting from where you are, to say, well, where does this, keep sliding this one down until it's fallen into the right place. So we'll move over the 92, in this case to make space for the 45. And then that's kind of the whole iteration on that first time. The next time we have to look at 67. Well, 67 is definitely going to go past 92, but not past 45. 41 is going to need to go 3 full iterations to slide all the way down to the front. 74 is just going to go over one number. Just needs to slide past 1. So on different iterations, right, a little different amount of work is being done, right? This loop terminates when the number has been slotted into position. We won't know in advance how far it needs to go, but we go all the way to the end if necessary, but then kind of sliding each one up by 1 as we go down. So that one moved all the way to the front. 87 just has 1 to go. 8's got a long way to go, all the way down to the very front there. 67 goes and stops right there. 15 almost to the bottom. And then 59 moving down this way. So kind of immediately you get the sense that it actually is doing something different than selection sort. Just visually, right, you're seeing a lot more movement for a start. That elements are getting kind of shuffled over and making that space. So it's definitely making a different algorithmic choice in terms of comparison versus moving than selection sort did, which is kind of a lot of looking and then a little bit of moving. It's doing kind of the moving and the looking in tandem here. If I want to hear how it sounds, because nothing's complete without knowing how it sounds. I can go back over here. And let me turn it down a little bit. So you hear a lot more work in terms of moves, right? Because of the thing, I'm going to speed it up just a little bit. So you see this kind of big cliff or sort of mountain sort of edging its way across as it goes, and then a lot of work is being done in the process of that moving, right? As it slides that thing down into position, finding its home. Some of them have kind of a long distance to travel, like that last one. Other ones are very close to where they go, don't have nearly as far to go on their turn. That's kind of cool. I'll crank it up to like a sort of a bigger number, let's say, and turn off the sound and just let it go. And you can kind of get a sense of what it looks like. It seems to move very, very quickly at the beginning and then kind of starts to slow down toward the end. If I compare that to my friend the selection sort, that it looks like insertion sort is way out in front and is going to just win this race hands down, but in fact selection sort kind of makes a really quick end run around it at the end, and actually came in just a few fractions of a second faster by kind of speeding up toward the end. So it's a little bit like the tortoise and the hare. It looks like insertion sort's way out in front, but then actually selection sort manages to catch up. I'm going to come back and look at these numbers in a second, but I'm going to go back and do a little analysis on this first. If you take a look at what the code is doing and talk about kind of what's happening, right? We've got a number of iterations of the outside, which is sliding each element's position. This inner loop is potentially looking at all of the elements to the left. So on the first iteration, it looks at 1. At the second iteration, it looks at 2, the third one 3, and so on. So the final one could potentially have n minus 1 things to examine and move down. If that element was the smallest of the ones remaining, it would have a long way to travel. But this inner loop, right, unlike selection sort that has kind of a known factor, it's actually a little bit variable because we don't know for sure how it's going to work. Potentially, in the worst case, right, it will do 1 comparison move, 2 and 3 and 4 all the way up through those iterations, which gives us exactly the same Gaussian sum that selection sort did. 1 plus 2 plus 3 all the way up to n minus 1 tells us it's going to be n squared minus n over 2, which comes down to O of n squared. That would be in the absolute worst case, right, situation where it did the maximum amount of worst. What input is the embodiment of the worst case for insertion sort? What's it got to be? If it's flipped, right, if it's totally inverted, right, so if you have the maximum element in the front and the smallest element in the back, right, every one of them has to travel the maximum distance in this form to get there. What is the best case? What does do the least amount of work? It's already sorted. If it's already sorted, then all it needs to do is verify that, oh, I don't need to go at all. So it actually, the inner loop only does one test to say, do you need to move over at least 1? No. Okay, so then it turns out it would run completely linear time. It will just check each element with its neighbor, realize it's already in the right place relative to the left, and move on. So in fact, it will run totally quickly, right, in that case. And then in the average case, you might say, well, given any sort of random permutation of it, each element probably has to go about half the distance. Some have to go all the way, some don't have to go very far, some go in the middle. You would add another factor of a half onto the n squared, which ends up still in the big O, just being lost in the noise. You say, well, it's still n squared. But it probably does, it is probably a little bit less of an n squared than selection sort. So if I go back here to my tool that was counting for me, that the mix of operations between insertion sort and selection sort, so that selection sort on the top and insertion sort that's beneath it, shows that selection sort is doing a lot of compares. In this case, I had about 500 elements, and it's doing about n squared over 2 of them, 250,000 divided by 2 there. And so it really is doing a full set of compares, a full n squared compares. It's doing a small number of moves. In this case, each element is swapped, so there's actually 2 moves, 1 in, 1 out. So it does, basically a number of moves that's linear relative to the number of elements. The insertion sort, though, is making a sort of a different trade-off. It's doing a move and a compare for most elements, right, in tandem, and then that last compare doesn't do a move with it. So those should be roughly tracking in the same thing, but they look closer to n squared over 4, showing that kind of 1/2 expected being thrown in there. But in the total, the idea is that it does about 100,000 compares and moves. This one does about 100,000 compares that when you look at them in real time, they tend to be very, very close, neck and neck on most things. So if I do this again, giving it another big chunk and just let it go. Again, it looks like insertion sort's off to that early lead, that if you were a betting person, you might be putting your money on insertion sort. But selection sort is the ultimate comeback kid. And toward the end, just really gets a second wind. And in this case, beat it by a little bit bigger fraction this time. If I put the data into partially sorted order. So now in this case, I've got about half of the data already where it's supposed to be and another half that's been randomly permuted. And now let it go. Insertion sort takes an even faster looking early lead. And selection sort, in this case, never notices that the data was actually in sorted order. The time actually is a little bit artificial here, and that in fact the number of comparisons is maybe a better number to use here, that it really did a lot more work relative to what insertion sort did, because insertion sort was more able to recognize the sortedness of the data and take advantage of it in a way that selection sort totally just continued doing the same amount of work always. So that's kind of interesting to note, right, is that when we're talking about all these different sorting algorithms, right, that we have multiple algorithms because actually they really do make different trade-offs in terms of where the work is done and what operation it prefers and what inputs it actually performs well or poorly on. That selection sort is good for, it does exactly the same amount of work no matter what. If it's in sorted order or reverse sorted order or random order, right, it always is guaranteed to do the kind of same amount of work, and you don't have any unpredictability in it. That's both an advantage and a disadvantage, right? On the one hand, it says, well, if you knew that you needed this sort to take exactly this time and no better, no worse would be fine, then actually having that reliable performer may be useful to know. On the other hand, it's interesting to know that in insertion sort, if you gave it to the data that was almost sorted, that it would do less work, right, is an appealing characteristic of that. And so having there be some opportunity for it to perform more efficiently is nice. The other thing also is about this mix of operations, whether it considers comparisons or moves a more expensive operation. For certain types of data, those really aren't one-to-one. That a comparison may be a very cheap operation and a move may be expensive or vice versa, depending on kind of the data that's being looked at. For example, comparing strings is often a bit more expensive than comparing numbers, because comparing strings has to look at letters to determine when they distinguish. If you had a lot of letters in the front that were overlapping, it takes sort of more work to distinguish at what point they divide and which one goes forward. On the other hand, moving a large data structure, if it were a big structure of student information, right, takes more time than moving an integer around. And so depending on what the data that's being looked at, there may actually be a real reason to prefer using more comparisons versus moves. And so examples I often give for this, like if you think about in the real world, if you were in charge of sorting something very heavy and awkward, like refrigerators, you're trying to line up the refrigerators by price in the warehouse or something, you would probably want to do something that did fewer moves, right? Moves are expensive. I'm picking up this refrigerator, I'm moving it. I don't want to move it more than once, right? And so you might want to go with a selection sort where you go and you figure out who's the cheapest fridge. Let me pull that one and get it over here. And now I'm not going to touch it again. Rather than kind of sitting there with your insertion sort and moving the fridges one by one, until you got it to the right spot. But if I were in charge of finding out who was, let's say, the fastest runner in the mile in this class, you probably would not enjoy it if my strategy would be to take two of you in a dead heat and say, run a mile and see who won. And now whoever won, okay, well, you get to run against the next guy. And if you win again, you get to run against the next guy. Like, you might just say, hey, how about you let me get ahead of that person if I beat him once? I don't want to have to go through this again. Like, doing fewer comparisons would certainly be preferred. So both of these, I would say, are pretty easy algorithms to write. That is certainly the strength of selection and insertion sort. They are quadratic algorithms, which we're going to see is not very tractable for large inputs, but the fact that you can write the code in 8 lines and debug it quickly and get it working is actually a real advantage to these. So if you were in a situation where you just needed a quick and dirty sort, these are probably the ones you're going to turn to. So just some numbers on them, right, is 10,000 elements on my machine, kind of in a unoptimized context, was taking 3 seconds. You go up by a factor of 2. We expect it to go up by about a corresponding factor of 4 in the time. It roughly did. Going up by another factor of 2.5, again going up. By the time you get to 100,000, though, a selection sort is slow enough to really be noticeable. It's taking several minutes to do that kind of data. And that means if you're really trying to sort something, of sufficiently large magnitude, a quadratic sort, like insertion sort or selection sort, probably won't cut it. So here's an insight we're going to kind of turn on its head. If you double the size of the input, it takes 4 times as long. Okay, I can buy that, right? I went from 10 to 20 and went up by a factor of 4. So going in that direction, it feels like this growth is really working against you, right? It is very quickly taking more and more time. Let's try to take this idea, though, and kind of turn it around and see if we can actually capitalize on the fact that if I have the size of the input, it should take 1/4 the amount of time. So if I had a data set of 100,000 elements, and it was going to take me 5 minutes if I tried to sort it in one batch, if I divide it into two 50,000 element batches, it will take just a little over a minute to do each of them. Well, if I had a way of taking a 50,000 sorted element and a 50,000 sorted input and putting them back together into 100,000 combined sorted collection, and I could do it in less than 3 minutes, then I'd be ahead of the game. So if I divided it up, sorted those guys, and then worked them back together, and if it didn't take too much time to do that step, I could really get somewhere with this. This kind of turning it on its head is really useful. So let's talk about an algorithm for doing exactly that. I take my stack. I've got a stack of exam papers. Maybe it's got a couple hundred students in it. I need to just divide it in half, and I'm actually going to make the easy, lazy decision about dividing in half is basically just to take the top half of the stack, kind of look at it, figure out about where the middle is, take the top half, and I hand it to Ed, and I say, Ed, would you please sort this for me? And I take the other half and I hand it to Michelle, and I say, would you please sort this for me? Now, I get Ed's stack back, I get Michelle's stack back. They're sitting right here. All right, so that was good because they actually took a quarter of the time it would have taken me to do the whole stack anyway. So I'm already at half the time. What can I do to put them back together that realizes that because they're in sorted order, there's actually some advantage to reproducing the full result, depending on the fact that they were already sorted themselves. So if I look at the two stacks, I can tell you this, that someone over here starts with Adams, and this one over here starts with Abbott. The very first one in the output has to be one of the two top stacks, right? They can't be any further down, right? This is the sorted left half, this is the sorted right half, right? That the very first one of the full combined result must be one of those two. And it's actually just the smaller of the two, right? So I look at the top two things, I say Abbott, Adams. Oh, Abbott precedes Adams. Okay, well, I take Abbott off and I stick it over there. And so now that exposes Baker over here. So I've got Adams versus Baker. And I say, oh, well, which of those goes first? Well, Adams does. I pick Adams up and I stick it over there. So now that exposes, let's say, Imellaglue, my old TA. Imellaglue and Baker. And I say, oh, well, which of those? Imellaglue. And at any given point, right, there's only two I need to consider for what could be the next one. And so as I'm doing this, what's called the merge step, I'm just taking two sorted lists and I'm merging. So I'm kind of keeping track of where I am in those two vectors, and then taking the top of either to push on to this collection I'm building over here, and I just work my way down to the bottom. So that merge step, right, is preserving the ordering, just kind of merging them together into one sorted result. If I could do that faster, then I could have actually sorted them. I'm actually ahead of the game, and there's a very good chance for that because that, in fact, is just a linear operation, right? I'm looking at each element, deciding, and so I will do that comparison n times to decide who goes next, right? I look at this versus that, and I put it over there. I look this versus that, put it over there. Well, I'm going to do that until this stack has n things in it. All of them have been moved. So in fact, it will take me n comparisons to have gotten them all out of their two separate stacks and into the one together. So it is a linear operation to do that last step, and we know that linear much quicker to get the job done than something that's quadratic.
Great.
Yeah.
When you merge the halves, are you taking the higher one in the alphabet or the lower one?
Well, typically I'm taking in the order I'm trying to sort them into, right, which is increasing. So it'll typically start at A's and work my way to Z's, right? So it turns out it's completely,
It doesn't really matter.
it doesn't really matter is the truth, but whatever order they're sorted in is the order I'm trying to output them in. So in fact, these are the, if they're first on the sorted piles, then they'll be first on the output pile. So whatever that first is. So I'm gonna actually go look at the code for a second before we come back and do the diagramming. We'll go over here and look at the stepping part of it. So this is the code that's doing merge sort, and so it has a very recursive flavor to it. It does a little calculation here at the beginning to decide, how many elements are going to the left and to go to the right. As I said, it does no smart division here. So this is called an easy split hard join. So the split process is very dumb. It says figure out how many elements there are, divide that in half, take the ones from 0 to the n over 2 and put them in one separate subvector, take the ones from n over 2 to the n and put them in a second subvector, and then recursively sort those. So let's watch what happens here. It computes that, and it says, okay, copy a subvector of the first, in this case 4 elements, copy a subvector that has the second 4 elements, the second half, so I've got my left and my right halves. And then it goes ahead and makes a call onto merge sort, which says merge that left half and merge that right half, and then we'll see the merge together. So I'm going to watch it go down, because the thing that's going to happen is when I do a merge of this half, it's kind of like it postponed these other calls, and it comes back in and it makes another call, which does another division into 2 halves, so taking the 4 that are on the left and dividing them into a 2 and 2. And then it says, okay, and now merge the left half of that, which gets us down to this case, where it divides them into 1 on the left and 1 on the right. And then these are the ones that hit my base case, that an array of size 1 is trivially sorted. So in fact, the merge sort never even goes into doing any work unless there's at least 2 elements to look at. And so when it makes this call to the merge the 45, it will say, okay, there's nothing to do. And then it'll merge the 92, merge sort the 92, which also does nothing. And now the code up here is going to flip. So be warned about what's going to happen here. Is I'm going to show you what the process of the merge looks like, which is going to do the left-right copy to the output. So this code looks a little bit dense And again, this is not the time to get really worried about what the details of the intricacies of the code are. I think you really want to kind of step back and say, conceptually, the process I described of taking them off the two piles and merging them is very much the take-home point for this. And so what this upper loop is doing is it's basically saying, well, while the two stacks, the two piles, the two halves, whatever, each have something left in them, then compare them and take, the smaller one off the top. So it's keeping track of all these indices, right? The indice of the left subarray, the indice of the right subarray, and the indice of the output array. And it's actually kind of, at each step, it's putting a new one, copying one from one of the left or the right onto the output. And so that upper loop there said, is 45 less than 92? It is, right? So it copies 45. And then at this point, right, there's nothing left on the left, so it actually drops down to those last two pieces of code, which actually do to copy the remainder from, if there's only one stack left, then just dump them all on the end. And so we'll do the dump of the end of the 92. And say, okay, I've reassembled it. And so when I get back to here, then I have merge sorted the left side. And then I go through the process of merge sorting the right side, which copies the 62 and the 41 down to those things, and then does a merge back. Let me get to the stage where I'm starting to do a little bit bigger merges. And so here I am with an indice on my left and my right side, and then my output index. And it's like, okay, is 45 less than 41? If so, then take 41 here and kind of advance P2 over. And so you'll see the 41 go across. And it moved both the P and the P2 up an index to say, okay, well, now we're ready to pick the next one. So it looks at P1 versus P2s, decides it's pulling from the left side this time. And then now it still has the last most members of the two piles to look at, takes from the right side, and then we'll just dump the end of the other side. So then going through this process, we do it all again, kind of breaking all it down. So it's just using recursion at every stage. So at the small stages, it's a little bit hard to figure out what's going on. But once it gets back to here, right, it's just doing the big merge. I let it go a little too fast there to build it back up. So there's one thing about merge sort I should mention, which is merge sort is using extra storage. And I'm going to get to a stage where I can explain why that's necessary. But selection sort and insertion sort both work what's called in place. And that means that they are using the one copy of the vector and just rearranging things within it. So it doesn't require any auxiliary storage to copy things over and back and whatnot. That it can do all the operations on one vector with a little bit of a few extra variables around. That merge sort is really making copies. That it divides it into these two subarrays that are distinct from the original array and then copies them back. So it copies the data away and then it copies it back in. And the reason for that actually is totally related to what's happening in this merge step. That if I had, actually this is not the step that's going to show it, I'm going to show it on this side. That if it were trying to write over the same array, I made it go too fast, and that was really very annoying. All right, let me see if I can get it one more time to be where I wanted it. Is that when it's doing the copying, if it were copying on top of itself, it would end up kind of destroying parts of what it's working on. I see why we're going to get this mistake the whole time. Okay. Is that as it was doing the copy, right? If this really were sitting up here and this really were sitting up here, if we were pulling, for example, from the left side, we would be overwriting something that was already pulling from the right side. I'm sorry, we'd be overwriting something that was on the left side, and so if it did that, it would have to have some other strategy for them. Well, where did it put this one that it was overwriting? Like if it's pulling from the left side, it's actually fine for it to overwrite in the output array, but otherwise, right, it would be writing on something it was going to need later. And so the easiest thing for merge sort to do is just to move them aside, work on them in a temporary scratch space, and then copy them back. There are ways to make merge sort in place, but the code gets quite a bit more complicated to do that. So your standard merge sort algorithm does use some auxiliary storage that's proportional to the size of the array. So that ends up being a factor in situations where you're managing a very large data set, where in fact maybe it requires, right, a large amount of memory already for the one set. Making a duplicate copy of it to work on may actually cost you more than you can afford. And so merge sort sometimes is ruled out just because of its memory requirements, despite the fact that it has a performance advantage over insertion sort and selection sort. What does it sound like, though? That's what you really want to know. So let's first just watch it do its thing. And so you'll see it kind of building up these sorted subarrays, kind of working on the left half and then postponing the right and coming back to it. And so you'll see little pieces of it and then little merge steps as it goes along. And then you can get a little glimpse of, kind of the divisions down there. Let me actually run it again, a little bit bigger thing. I'll turn on sound in just a second, just like as it goes faster and faster. Let me make my sound go, and we'll see how much we can stand of it. It's pretty noisy, you'll discover. Volume? Can we have a little volume? Oh yeah. Yeah. A lot of noise. Oh yeah. Okay. So you definitely get the kind of 1960s, sound tone generation there, but you get this idea. You can hear the merge step, right, is very distinguishable from the other activity. As it's doing the kind of smaller and smaller subarrays, it sounds just a little bit like noise. But as you see the larger subarrays being joined, this very clear merging sound emerges from that you can hear and see that. And at the very end, sort of one big long merge of taking the two piles and joining them into one. A lot of noise, right? So that should tell you that there is a pretty good amount of movement going on. Question?
When does it decide to merge them?
So it's merging them after they've been sorted. So when you see a merge, you'll always see two sorted subarrays being joined into one larger sorted subarray. So at the very end, for example, you'll have these two sorted halves that are being merged down.
And how much is it sorted?
Well, it's recursion, right? It's like it sorts the half, which sorts the quarters, which sorts the eighths. And so at any given point, what it really looks like it's sorting is these little one-element arrays, which are being merged into a two-element array. Like all the work is being done in merging, really. That sorting, it's kind of funny. When does it actually sort anything? Like never, actually. It only merges things. And by dividing them all the way down into all these one-element arrays, the merging of them, it says, well, here's these trivially sorted things. Make a two-element sorted thing out of them. And now you have these two-element things, merge them into one four-element thing, which you merge into an eight-element thing, and all the way back. So all of the work is really done in the merge step. Kind of on the sorting angle, it actually is deferring it down to the very bottom. So that's a kind of an odd thing to do, right? It really just divides it all up into one, 100 piles, each of size 1, and then kind of joins those into one pile, these into one pile, these into one pile, and so now I have 50 piles, right? That are each of size 2. Now I join them into 25 piles of size 4, and then 12 piles of size 8, and so on. So this is the code for the outer point of the merge algorithm. I'm actually not going to look at the merge algorithm very in depth. I'm really more interested in the kind of outer point of this algorithm. And so the steps that are going on here is we do a little bit of constant work. Let me actually. We do a copy operation that copies out the left half and the right half. Both of those operations together require linear time. So I've looked at every element, and I copied the first half onto something, the second half onto something. So that took, I looked at every element in that process. I make two calls on the left and the right side, and then I do a merge on the end. And we talked earlier about how that was linear in the number of elements, because as I build the two piles into one sorted pile, every element is touched in that process as it gets chosen to be pulled out. So linear divide, a linear join, and then there's this cost in the middle that I have to kind of sort out what's happening, which is there's sort of n work being done at this level, but then I make two recursive calls that should take time n over 2. So the input they're working on is half again as big as the one I have. How much time do they take? Well, there's my recurrence relation that allows me to express it. T of n is n. So at this level, this kind of represents the copy step and the merge step at this level, plus the work it took to get the two halves in sorted order. So I'm going to show you a slightly different way of looking at recursive analysis, just to kind of give you different tools for thinking about how to do this. I showed you last time how to do the repeated substitution and generalization of the pattern. I'm going to show you this way to do it with a little bit of a tree that kind of draws out the recursive calls and what's happening in them. The merge sort of a input of size n does n work at that level, the copy in the merge step right for there, plus it does two calls to merge sort of n over 2. Well, if I look at each of those calls, I can say, well, they contribute an n squared and an n squared on each side. So this one has n squared copy and merge. This one has an n squared copy and merge. And so in effect, I have another n squared plus itself there. And then this level, right, looks at the n over 4, which has 4 n over 4 components, so that actually at each level in the tree, that every element, right, is being processed in one of those subcalls across it. So every element is up here, and then they're in 2 subgroups, and then 4 subgroups, and then 8 subgroups. And that each element is copied and merged in its own subgroup at each level of the recursion. So that kind of gives me this intuition that there's sort of n work being done on every level. Every element copied and merged as part of that there. And so then what we need to complete this analysis is to know how deep this tree grows, how far we get down in the recursion before we hit the base case. So we're dividing by 2 each time, n over the 2, over 2 to the second, 2 to the third, 2 to the fourth, and so on. So at any given level, k down, right, we have n divided by 2 to the k. What we want to solve for is where n over 2 to the k equals 1. So we've gotten to the smallest case where we have those trivially sorted one element inputs to look at. And so we just do a little math here, rearrange that, right, divide by 2 to the k, or multiply by 2 to the k both sides. We have n equals 2 to the k, take the log base 2 of both sides, and it will tell me that k is log base 2 of n. That I can divide n by 2 k times, where k is the log base 2 of n, before it bottoms out with those one element vectors. So log n levels, n per level, tells me the whole thing is n log n. So n log n is a function that you may not have a lot of intuition with. You may not have seen it enough to kind of know what its curve looks like. But if you remember how the logarithmic curve looks, right, which is a very slow-growing, almost flat line, and then n being linear, the kind of combination of the two, it's called the linearithmic term here, is just a little bit more than linear. Not a lot more, but it grows a little bit more steeply than the standard linear was, but not nearly, right, as sharply as something that's quadratic. So if we look at some times that selection sort compared to merge sort, right, on a input of 10,000, right, took a fraction, right, to do a merge sort that it did to a selection sort, and as it grows, right, so if we go from 20,000 to 50,000, we've a little bit more than doubled it, that the merge sort times, right, went up, you know, a little bit more than a factor of 2 in growing in these things. Not quite doubling, a little bit more than doubling, right, because of the logarithmic term that's being added there, but growing, you know, slowly enough that you could start imagining using a sort like merge sort on an input of 1,000,000 elements in a way that you cannot on selection sort, right? Selection sort, my estimate, I did not run it to find this out, right? Based on the early times, I can predict it'll be about 8 hours for it to sort 1,000,000 elements, taking just a few seconds, right, for merge sort to do that same input. So a very big difference, right, from the n squared to n log n that makes it so that if you have a sufficiently large data set, right, you're going to have to look to an n log n sort, where an n squared sort would just not work out for you. I'll mention here that actually n log n is the theoretical boundary for what a general purpose sort algorithm can do. So that our search from here will have to be a quest for perhaps an n log n that competes with merge sort and maybe exceeds it in some ways by having lower constant factors to it, but we won't get a better big O for a general purpose sorting algorithm. If we have to sort kind of any amount of data in any permutation, and it has to work for all cases, then n log n is the best we can do in terms of a big O. Let me show you these guys kind of running a little race, because there's nothing more important than having a reason to bet in class. So if I put insertion and selection and merge sort all up against one another, let's turn off the sound, because I really don't want to hear it all go. So merge sort, just really smoking. And insertion sort and selection sort, you know, not giving up early, but definitely doing a lot more work. So if you look at the numbers here in terms of comparisons and moves that are being done in the merge sort case, right, so I have 500 elements here, is, you know, substantially less, right, than the quadratic terms that we're seeing on the comparison and move counts, right, for selection sort and insertion sort. And so this is still on something fairly small, right, 500 elements, right? You get into the thousands and millions, right, the gap between them just widens immensely. Does merge sort make any good sense out of things being already sorted? So thinking about what you know about the algorithm, does the fact that it's mostly sorted or already sorted provide an advantage to the way merge sort works? Nope. Nope, just not at all, right? In fact, if I can make the data actually totally sorted for that matter, right? And say, go ahead and sort, see what happens, right? And it's like, insertion sort did 511 comparisons, 0 moves, realized everything was in sorted order and finished very quickly. Merge sort still did a lot of work, thousands of comparison moves. It did a slightly fewer number of compares than it would typically do. That's because when it, for example, it divided into the left half and the right half, it had all the smaller elements on the left, all the larger elements on the right, and it will sit there and compare to realize that all of the left elements go first, and then it'll kind of just dump the remaining ones on. So it actually shaves off a few of the comparisons in the merge step, but it doesn't really, provide any real advantage. It still kind of moves them away and moves them back and does all the work. And then selection sort just still taking its favorite amount of time, which is, I'll look at everything. That might be the smallest, but I'm not taking any chances. I'm going to look through all of them to make sure before I decide to keep it where it was. If I put them in reverse sorted, just because I can. You can watch insertion sort bog down into its worst case, and that gives selection sort a chance to show its mettle. And there's selection sort showing, okay, well, if you give me my absolute worst input, I definitely do have a little bit more hard time with it. But merge sort still just doing its thing. What if I make all the sound go on? Just because we can. Because really I have 2 minutes and I'm not going to start quick sort. Ah, like they're juking it out. Oh no! That sounds like a cartoon, sort of road race. I could watch this thing all day. In fact, I often spend all day. I show this to my kids. I'm still waiting for them to come up with the next great sort algorithm, but so far, really, it's not their thing. So I will give you a little clue about what we're going to do. We're going to do next is talk about a different recursive algorithm. Same divide and conquer strategy, kind of overall, but kind of taking a different tactic about which part to make easy and which part to make hard. So merge sort, as I said, did this easy split hard join. We divided them in half using sort of no smart information whatsoever, and then all the work was done in that join. I've got these two sorted piles. I got to get them back into order. How do I work it out? Well, the quicksort algorithm is also recursive, also kind of a split join strategy, but it does more work up front, deciding that in the split phase, if I kind of did a more intelligent division into two halves, then I could make it easier on me in the join phase. And its strategy for the split is to decide what's the lower half and what's the upper half. So if I were looking at a set of test papers, I might put the names A through M over here. So go through the entire pile and do a quick assessment of, are you in the upper half or the lower half? Oh, you're in the lower, you're in the upper. These two go in the lower, these two go in the upper. I examine all of them and I get all of the A through M's over here, all of the N through Z's over there. And then I recursively sort those. So I get the A to M's all worked out, I get the N through Z's all worked out. Then the task of joining them is totally trivial, right? I've got A through M, I've got N through Z. Well, you just, push them together. There's actually no comparing and looking and merging and whatnot that's needed. That join step is where we get the benefit of all the work we did in the front end. That split step, though, is a little hard. So we'll come back in on Friday and we'll talk about how to do that split step and then what are some of the consequences of our strategy for doing that split step and how they come back to get at us. But that will be Friday. There will be music. There will be dancing girls.